Dear all, welcome to this webinar facilitated by the Climate Resilient Sustainable Road Pavement Surfacing's CRISPS project team. My name is Nicole Mietje and I'm the team leader at the University of Birmingham. But CRISPS is a research project funded by the UK's Foreign Commonwealth and Development Office and managed by IMC worldwide through the High Volume Transport Applied Research Programme. This is a 5-year research programme funded by DFID to increase access to transport services, more affordable trade routes, and safer, lower carbon transport in low-income countries. CRISPS is an 18-month multidisciplinary research project which aims to demonstrate the technical and economic suitability of 3 global best practice road surfacing technologies for the range of traffic and environmental conditions of high volume roads that typically currently occur in low income countries and those that are predicted to occur in the future. The CRISPS project includes partners from the University of Birmingham, the International Roads Federation, Universiti Putra Malaysia and the University of Auckland, who will be leading this webinar. Today's webinar covers an introduction to the Epoxy Modified Bitumen performance, as you can see on the screen, from laboratory tests, trials and applications to date. It also provides the methodology used for calibrating HDM4 deterioration models using long-term performance program data and laboratory results. I'm absolutely delighted to be joined today by Teuns Henning and David Alabaster. Dr. Teuns Henning is a senior lecturer at the University of Auckland. He's also a founding member of the Climate Adaptation Platform, specializing in asset management, performance monitoring, climate adaptation, performance-based contracts, and benchmarking. And David Alabaster is a principal pavement engineer with Waka Kotai and manages the Captive Road Research Centre in Christchurch. In addition to managing Captive, David is responsible for the development and revision of road construction specifications and pavement design guides. The webinar will be recorded for academic use. So therefore, without further delay, I will pass over to the first of our speakers, Teuns Henning. If you have any questions, please put them in the question and answer section of Zoom. Thank you very much, and hopefully you enjoy the presentations. Over to Teuns.
Thank you very much, Nicole. Thank you for this opportunity. Welcome to everybody that joins us today. Good morning, good afternoon, and good evening from New Zealand. So I have a few slides, and then I'm going to get David Alabaster to do most of the presentation tonight. David has been the person that pushed the epoxy technology in New Zealand and has been in the leading edge of that. So we've just felt it was appropriate for him to introduce some of the work that they have been doing in the development of both the porous asphalt using epoxy modified bitumen and also chip seals. Thank you. First slide, please. So Nicole has kindly introduced the program to you. So the CRISPS program is run out of Birmingham as lead institute, and then us, the University of Auckland and the University in Malaysia, UPM, are contributing towards this research. It is about an 18-month multidisciplinary research project, and really the aim is there to demonstrate the economic sustainability of these climate resilient technologies for surfacing. Our focus is on the high volume road spectrum, but we're really looking at a range of traffic application and the environment. On the right hand side there, some of you may have attended the earlier webinars that we've done, so we have gone into that in a bit of detail. So just for the newcomers here tonight, we've got the main work areas being first to develop deterioration modeling, understanding how these surfaces perform over time. We also are looking at other types of additives from the university in Malaysia. In particular, we're looking at fiber reinforced asphalts and really want to see how that perform over time. From that, we want to do the life cycle analysis to understand the economic viability of this technology. And then, of course, for our application, and particularly in some countries in Africa, we've got to also look at the constructability and make sure that it is a technology that is sustainable within that environment. Thank you. Next slide, please. So just to stand back a little bit in terms of what we are trying to achieve with building in a little bit of resilience into our road networks. What we have there is the classical resilience curves. And you see there two curves, curve A, the green one, and then the blue one, curve B. So when we look at either a shock event, weather event, or climatic impacts, or even slow changes in time, we know that we get a massive reduction in the serviceability of our infrastructure. In this case, we may be talking about roads or bridges. So what we try to achieve with the infrastructure is to improve that resilience, so that number one, when there is a shock event, that you don't lose too much functionality. And of course, the more your infrastructure is able to cope with shock events, the shorter your time of recovery is also going to be. There is naturally also another secret in that figure, is that when we do good asset management, when we look after our infrastructure, well looked after infrastructure is by nature also more resilient. So we are going to look at all those aspects, but tonight's topic is really about how the climate resilient surfaces can help in that. Thank you. Next slide, please. So in terms of looking at the climate impacts, and I've used this slides a few weeks ago in a presentation with the TRL in the rewrite of Road Note 29, we know that there's a number of things that can happen to road pavements in particular with weather events. And the main purpose, of course, of our surfacing is to provide a durable surface to ride on, but then also primarily to keep the water out of our pavements. So having that surface being waterproof all the time is really a secret in maintaining the roads. Now, I'm sure that many of you have been taught that one of the number one enemies to road pavements would be water, and that's clearly illustrated with the two figures on the right-hand side. David is going to talk about the Canterbury Accelerated Pavement Testing Program. Now, those results came out of that program where we've looked at how different pavements perform under different moisture conditions. And as we can see clearly there, the bottom figure with a saturated, undrained soil, when you start loading up the pavement with higher state loading conditions, it's just failing fast. So when we then look at the different climatic impacts on the left-hand side, we see an array of things that we need to keep in mind when we do design our surface in different parts of the world. The main focus areas for us tonight is going to be certainly on keeping it watertight. So we want to make sure that increased rainfall is not going to impact on our surface, and also extreme weather conditions. And for many of those of you that comes from different parts of the world, like Africa, we know that the number of very hot days are increasing, and obviously that impacts on our bitumen by decreasing the viscosity, and also over time increase the hardening of the bitumen through the oxidation process. And that is some of the things that we would like to address with our epoxy modified bitumen. Thank you. Next slide. So again, this slide has been showed before, and it demonstrates the process we want to follow in developing deterioration curves for our epoxy modified surfaces, and also the fiber surfaces that we're going to look at. Now, unfortunately, we don't have long history of performance data over time that's normally used in the development of performance curves. So we have devised a structure of looking at relativity in performance. So we're going to do, first of all, look at some of the lab results that David will explain in a moment, and see how it compares to our traditional pavement surfaces in New Zealand. We will calibrate the New Zealand pavements to the HDM models, and then use techniques to adjust those models to incorporate the lab results on the epoxy surfaces. Likewise, we're going to have a relative performance difference between New Zealand conditions and those in Ethiopia, to also get equivalent shift in performance curves between what we have in New Zealand and what we have in Ethiopia. We are fortunate that there were some trials set up in Ethiopia that's been monitored over time. So we do have a little bit of performance data that we can then compare to. Now, with all of those relative shifts in our curves, we will be able to provide deterioration models as closely as we can for these modified surfaces. Thank you. Next slide. So for the New Zealand performance, we are going to use the New Zealand long-term pavement performance data. This program was established about 22 years ago with roughly around 160 odd sites scattered around the country. So on the right-hand side, you see the map of New Zealand, the North Island and the South Island. And all of those dots represent where we've got some of these calibration sites. Now that calibration sites represents about 3 different climatic zones, and some of those zones obviously correspond very well with the ones that we have in Ethiopia. So it is possible to look a little bit at the relativity between those. On these sites, we have completed quite accurate manual surveys, both rutting, roughness, texture, and then detailed visual effects. And then in the middle is a typical layout of the LTPP sites. So they are all about 300 meters long, subdivided in 50-meter subsections. And we do the rutting measurements every 5 meters and do the roughness surveys in repeated roughness surveys in the wheel tracks as indicated there. Okay, so that is it from me. I'll now hand over to David to take us through an introduction of the epoxy technology and where we've got to with that in New Zealand.
Thanks, Chins. Good evening, everyone. Apologies, there's a plane just going past at the moment, and I'm just struggling with the technology a little to change slides. For some reason, it's decided it doesn't want to move on. I know the joys of technology. There we go. All right. As John has suggested, I will give a brief outline of what we've been doing in New Zealand with porous asphalt, trying to extend its life. And I'll also talk about our epoxy chip seals, which is also to solve a different problem, in that case, the flushing of those materials and the need to do maintenance. So my presentation on the porous asphalts will start with a discussion of the community focus that we have to basically the reason why we're doing the work. I'll also talk about our implementation of that material and also a little bit about sustainability. So to get started though, it's probably worth going back and having a review of the epoxy bitumen idea, where it's come from, and why we're chasing some of these ideas down. So the material, sorry about that. The material was developed by Shell in the 1960s for airfields, and particularly for allowing fighter jets to get off runways without melting them in the Cold War. So an interesting material. Its main use over the last, well, I suppose it's now 60 years, has been in orthotropic steel bridge decks. So they're quite difficult bridge decks to put asphalt on. And the reason everyone has got quite excited about these materials is that there's been bridge decks that have survived 40 years. So there's a track record of durability in these materials. It is, as you can imagine, a 2-part system. There's a part A, which is the epoxy resin, which is a clear fluid. And the part B is the curing agent, which has been mixed into a 70 pen grade bitumen. So this is a little bit different to your normal materials. Once this is mixed, it needs to be used, and it needs to be used relatively quickly. There's no reheating it. The reason everyone is, well, not everyone, the reason New Zealand has become interested in these materials and the Netherlands is dates back to an OECD research program back in the early 2000s. That research program found that epoxy modified bitumen was the only existing product with the potential to extend surface lives. This project was led on the epoxy side by the US Federal Highways Administration. It also included TRL, LCPC, ARB in Australia, and also BAST in Germany. So it's a well-funded, well-resourced program. The findings were that the epoxies were stiffer at service temperatures with greater load spreading. They were more resistant to rutting. They had better low temperature crack initiation, better surface abrasion from tire action, and that was even after oxidation. They were more resistant to fatigue cracking. They were less susceptible to water-induced damage, and for us particularly, they were more resistant to oxidation, and that was a major problem we were seeing. So we got fully on board when we realized it could solve quite a major problem for us. So our input into that program was to do some lab testing, and on the left you can see a sample that's been prepared, and right next to it is a sample that's been through what's known as a contemporary test, and that's simply a sample that's been oxidized by heating it to 85 degrees for a number of days and then put into the test drum. And the test's very simple. It is just looking at the mass loss that's occurred as the sample's been rotated in the drum. That showed us that we were on the right track with our porous asphalts, that this material could actually help. We then had to look at, could we make this material, which for New Zealand was actually quite a challenge. We weren't using the sorts of asphalt plants that epoxy asphalts were typically made with. They're normally made in a batch plant. We were using continuous drum plants. So we needed to go and actually have a go at this and see if it worked. And part of that was done at our accelerated pavement testing facility captive, which is obviously the figure down the bottom. And that work in 2007 showed us, yes, we could make these materials, and yes, they did appear to look very, very good. In terms of making the material, it's actually not that difficult. The photo on the top right shows basically an additional small tank for the part A of the material that's fed into, well, blended in with the part B material out of a normal line in the asphalt plant, and then it's just going into a mixing box once it's come out. So it is no harder than putting things like adhesion agents into plants, and we found from a practical point of view, we certainly could do this with very few problems. We then went out into the field to try this out on one of our state highways, State Highway 1, and we found that in terms of paving the material, there were no real problems in paving the material. So it was an eminently practical sort of material to use. So I suppose we need to get back to that question, why were we actually interested in doing this? It wasn't for the technical challenge. It was actually because our communities wanted safe, sustainable and quiet roads. And we could certainly make safe and quiet roads with our traditional porous asphalts. They were fantastic for noise. They were safe in wet weather. We knew we had about 6.5% of these sorts of surfaces on our network, but we knew that we were also building a lot of motorways and that we were going to double that amount of material over the next 5 years. The problem with them was they only last about 7 to 8 years on our network. That's makes it not particularly sustainable. They're expensive, costing $20 to $30 a square metre to replace. The interesting part was all the OECD partners had similar stories. A lot of them were getting longer lives, but they still weren't getting very long lives out of their surfacings. So we knew we had a safe and quiet surface, but sustainable it certainly wasn't. And that's where the epoxies came in. The testing we'd done in the laboratory suggested that we could actually get to sort of a 40-year life with the way we were doing it, which wasn't quite the same way as the OECD. We took a step further than the OECD and looked at just getting durability. We could do it for an extra $6 a square metre, which is obviously a tiny amount for the increase in performance. And that would give us a safe, quiet, and sustainable solution. So in terms of trying to present the abrasion results from the Canterbury test, we've normalized the results from an unaged sample to sort of present the benefits of putting the epoxy into the mix. The figure shows a sort of a black line and a blue line. They're conventional binders, both a conventional bitumen and a 4% SBS binder. SBS is very good, gives you an additional early strength. But what it doesn't do is, as you oxidize the sample, and in our case, we did it by increasing the temperature over a number of days, sort of 40 days at 85 degrees C is the equivalent of 8 years of aging in the field. When you do that, you see that the SBSs and the conventional materials do start to lose a lot of material in the Canterbury test, whereas the epoxies, either is the full strength material, the 100% epoxy used in bridges, or the 25% epoxy that we were using on the road, have got a substantially better performance. We also, the Canterbury test itself is very, very simple. So we also looked at additional abrasion tests and actually settled on a concrete test to look at the performance of the epoxies. And that is where we've aged the samples, we've tested the samples at 10 degrees C. We looked at different ways of having an abrasion test. We looked at rubber and polyurethane pads, but they just simply weren't strong enough to test it. So we actually used metal cutters out of the concrete testing and applied metal cutters to the surface after aging to see what would happen. And we ended up with very much the same rankings from the Canterbury test, which is what we were looking to support. And it really showed that the control material after aging certainly is a considerably poorer material than the 25% epoxy material, right the way through to the 100% sort of stuff that they use on bridges. And you can also see that using the polymers like the SBSs don't actually improve the durability of the material a great deal. We also did additional testing once we came into doing our own 25% epoxy blends. That was done on one of our large motorway projects in Christchurch in 2012, and that demonstrated that we really could use these materials. And one of the things we found with the 25% epoxies was that they were not only cheaper, that they were actually easier to manufacture, less scary for the asphalt plant owners, and they were actually easier to lay by the staff. In terms of implementation, we had our first normal production run in 2016. And so we've been doing this for 5 years now. And we've now laid these materials on our busiest sites up to 160,000 AADT, which is in one of our Auckland motorway pieces of road. We've got now over a million square meters of this material laid. Now all our main contractors are capable in all our main cities of using this material. We've also got the first New Zealand epoxy bitumen blend approved, which is really, really good to see. So that's actually a New Zealand contractor buying an epoxy and blending it with a bitumen that they've procured rather than buying a pre-blended epoxy bitumen from other suppliers. And one of the really great pieces to come out of our work was Dura Vermeer from the Netherlands came to New Zealand a couple of years ago to see what we were doing, and they've actually just finished their first project in the Netherlands, first full project, which is a ring road around Boekel, which coincidentally is my wife's family's hometown in the Netherlands, so quite convenient for keeping an eye on. I can send the family out to look at it. These ideas have also helped increase resilience, and they are delivering additional sustainability benefits. They actually weren't part of the original thinking, but by putting down a longer life product, you do get some benefits. So we've recently had a review by one of our consultants for our environmental team to see how we were tracking with the material. They felt that the CO2 equivalent of using this material was 29 to sort of 42% less than a conventional binder. So, but it did depend a bit on the epoxy source. In terms of whole of life aggregate and bitumen use, we are using 1/5 of the materials of a conventional log bit, because the conventional log bit needs to be replaced about every 8 years. So that in itself is a good saving. But when it came down to the maintenance costs, we were effectively doing this putting down our premium surface for 20% of the whole of life costs of our previous generation of low noise surfacings. So moving on to the epoxy modified chip seals. In this part of the presentation, I will again talk about our community focus. I'll talk a little bit about our lab work. I'll talk about our first hand-laid field trial and our full-scale construction. So the community focus here is exactly the same. You know, our communities want safe, sustainable, and quiet roads. It's a pretty reasonable want. One of our problems in our rural roads is that we use a lot of chip seal surfacings, or sprayed seals, as our Australian cousins will call them, and flushing, which is binder rise in the material, leading to problems with skid resistance, is a major problem. Some 30% of our resealing in 2010, 2011 was driven by flushed surfacings. The problem with these sorts of surfacings is they can lead to even more expensive treatments. At times we have to rehabilitate base courses just because there's so much bitumen on the surface that it becomes unstable, and we actually either need to bury it or dig it out. So this isn't a particularly safe or sustainable option when they're in this sort of condition. And based on the successes we'd seen on the epoxy ulpa, we thought the epoxy binders might help us. So we started working on an epoxy chip seal, hopefully with a 40-year life and hopefully safe and sustainable. So this is what I'm talking about in terms of flushing. I mean, it's fairly typical around the world, I believe. The binder coming to the surface of the stones and leading to a reduction in skid resistance. You can see in the figure in the top right photo, you can actually see that tire tread has actually squeezed the bitumen on the surface. Down the bottom left, you can see where this is one of our trial sites where we stopped traffic just before starting to spray. Actually had to stop the trial because we'd actually ripped up the chip seal surface and exposed the base course underneath. So this is an example of the sort of damage that can be done. And the real problem is you're using a heat sensitive material, and flushing and bleeding where the bitumen tracks down the road can have many causes, but it really is a massive problem, and particularly in hot weather, which is obviously something the climate adaptation platform wants to consider, right through to actually damaging the surface integrity. And our big focus on flushing particularly is even before those sorts of problems happen, the surfaces become unsafe in wet weather. So So the first bit of lab work was all about trying to see whether or not the epoxy bitumen would help at all. So we started off in the lab with some wheel tracking tests, and we basically made a little soft mastic made out of sand and bitumen as a base layer, and then we chip sealed over the top of it in the lab. On one side, on the left-hand photo, you can see what was a 180-200 control material, which is a conventional chip seal used in New Zealand, so nothing particularly special. And then we wheel tracked, well, we cured it for 10 days, then we wheel tracked it, and you can see a big black stripe down the middle of it, and you can see that it's not worked very well. Not that we were expecting it to work well. Then we did the same thing, but we used an epoxy chip seal with a 5% accelerator in it just to make it go off a bit faster. We did the same thing, we cured it for 10 days, then we gave it 12 hours of traffic at 35 degrees C, which isn't particularly hot by New Zealand standards. You know, 70 degrees is quite possible in surface temperatures, but this was just for testing. And you can see the epoxy's actually done a wonderful job in preventing the chips being pushed into the soft mastic underneath. So that gave us some confidence that we should actually try this idea and take it out into the field. So some of our initial work was actually, we did some labour-based methods to actually put the initial trials down. So the control were actually labour-based approaches, because that could guarantee that we'd actually mix the materials at the right quantities. And we did a lot of testing around that. The labour-based approach actually ends up with a faster cure, because you end up with some hotter binder for longer as you've mixed it. But what we were trying to do is work out a way where we could do this on a large scale for New Zealand conditions, which meant we tried impingement spraying, which is trying to just spray parts A and B together outside of a spray bar and see if that would actually cure well enough. And it certainly did. So in this case, we hand chipped the sections, we used some small rollers, and then we did some tensile tests to see how the curing worked, and the impingement spraying worked well. So then we moved on to taking this idea into the field. So we actually built a full-scale spray bar with impingement spraying. You can see the spray bar here. There's actually two sets of nozzles on the spray bar, and part A is being sprayed into part B, and then it's hitting the road, and then we do what we normally do. We chip it and we roll it. So this is no different to doing a normal chip seal. We're not waiting for it to cure. We're not doing anything like that. As soon as we've chipped it and rolled it, we'll move the traffic over and start doing the other side of the road. So it is just effectively a normal spray sealing operation. The only real difference is in the calibration of the machine. We traditionally hadn't used troughs for calibration. We do what we call a pad test, where we spray over pads, then pick up the pads and see how much they weigh to make sure the machine's working properly. We've had to add in a trough calibration to make sure the part A and part B are doing what they're meant to do. So when it comes to sort of trying to track, you know, how good a result are we getting? So we've got 2 trial sites down, and we've compared that against the sort of texture loss we see in traditional materials from our LTPP program, so a site with a similar traffic volume. And you can see here the blue line is the traditional line. It's got quite a steep slope on it. It's on a log scale. Sorry, a log scale, not a log scale. And the epoxy trial sites have got a much, the green and the orange lines, got a much flatter slope. So we're very definitely having a significant impact on the loss of texture in using this type of approach. And you've got to remember, these were on very poor performing sites that we applied this. The blue line is actually just a normal site and the texture loss that we would expect. So over to you, Chuns. I think you're finishing up for the last little bit.
Thank you very much for that, David. That was just excellent and interesting every time that I hear it. So the next steps for this program is to start developing the models that's going to give us that deterioration rate of the alternative surfaces. From that work, we will then be able to determine the life cycle cost aspects, because with climate resilient technologies, you need to know that you get that return on investment. And I think David already suggested to you that the evidence is there that we're going to have a good return on investment with this technology. And then we are also going to start in the new year with the trial constructions in Ethiopia. I understand that our material is on its way with the ship and almost ready. So we're going to do those trials as part of this program. So thank you very much for that. In the new year, you can look out for our next presentations on this program. I believe we're going to do one in around about March, and then perhaps one in later April. So we are looking forward to see you there again. And yes, I think we're now ready to take some questions.
Thank you very much both for two fantastic presentations and some excellent information. It's certainly triggered a number of questions, so I'll pass over some of the questions. So one is related to curing. So there are a couple of questions related to this. First of all, is heat not required for curing? And also, how long does the curing process take?
I'm guessing that's for me. Right. Yes, it doesn't require curing. The actual use of bitumen with the epoxy, the initial strength comes from the bitumen. So we're not actually curing materials at all. So in the epoxy ulpers, they just need to cool down as you do with a normal porous asphalt. You cool it down and then open it to traffic. And with the epoxy chip seals, it is precisely the same as a normal chip seal. You are just spraying it, chipping it, rolling it, and opening it.
And with that, there's another question: is solvent needed or solvent used for the epoxy bitumen?
No solvents are used.
Okay, thank you very much. I think, Tunes, you had a picture about your loading cycles on the graph where you had showed some of the aged material. So the question is, the loading cycles on the graph with materials of different moisture contents, what test was used for the loading cycles?
Okay, thank you. I'm actually going to refer to one of the slides that David has shown with the accelerated pavement tester in Christchurch. So we have had an experiment where we've looked at different surfacing practices and just see how it copes with water, both freestanding water, but then also the water under the pressure when the wheel spins around. And those tests that we've got there was actually part of that experiment in the accelerated load performance testing.
Okay, thank you very much. I've got a number of questions for David because of his excellent presentation. So the first one is, what lab setup or apparatus is used for conditioning the samples for the aging tests? Because you showed some aging tests. How did you actually age the samples?
So the samples are just aged at 85 degrees. So it's a really simple sort of approach for doing the aging. So it's a time and temperature relationship for aging. I know people can increase pressure to artificially age things as well, but we were doing big samples, and after many years of looking at it, came to the conclusion that just raising the temperature was the easiest thing to do.
And there was no influence or no change of moisture at all? It was just temperature?
Just temperature. So they just kept it in an oven for a long period of time for the epoxies. Yeah.
Okay. I've got another question for you. Is for porous asphalts, the concern in tropical countries is the rapid oxidation and subsequent cracking that will occur. Additionally, silt clogging the pores is another concern. Any in-service performance results for OGPA and EMOGPA roads in the tropics that show durability?
No, nothing in the tropics, unfortunately. But the oxidation problem is very much the problem that we're trying to solve. So if you're looking for a solution for the tropics, this would be the one I would be looking at.
Yeah, and maybe
Yeah,
if I can just add, to that, often what we get with the cleaning of the porous asphalt, you use is water spray under quite high pressure, and that sometimes can cause some damage to the surface, or at least faster deterioration. So I think the epoxy technology in that perspective is also a little bit stronger and more resistant. And I don't think there's any evidence that suggests which one will clog the fastest. I think that's a sort of an equal basis for both technologies.
Yeah, well, actually, from a clogging perspective, one of the interesting findings out of that initial trial that we did was some remarkably good noise properties coming out of the epoxies. For reasons which we haven't quite established, we've got quite a noise program going with a CPEX trailer to try and understand the noise benefits, and we've spent a lot of time optimizing the acoustic properties of these materials, but that's a topic of a different presentation, I guess.
Okay, moving in a slightly different direction, and with all interest in recycling, is a question about, can epoxy asphalt be recycled?
Ooh, yes, it can. So one of the things that we were asked was very much that question: can you recycle it? And there's been a lot of interest in that. We were we were the only place that had some material that had been down for a number of years. So we actually milled up part of our epoxy trial, basically the shoulder of it, to test out recycling. So we actually sent samples to the US and to the Netherlands to see if it is recyclable. It very definitely is. Even more exciting is that there's work being done with the epoxies to recycle traditional porous asphalts, and very high percentages. So there's a thought that we may be able to recycle up to 100% of asphalt with the epoxy type technology. 1 or 2% of epoxy should be all that's needed. So that's an exciting area of research that's going on at the moment.
That is exciting, and I think in the current environment and going forwards, that's really quite critical when we develop new materials and new approaches to things, to really think about the recycling and what we do after the end of life with the material. So I've got a number more questions. One is, can epoxy asphalt be installed over conventional asphalt pavement?
Yes. So, yep, we've done that. Yeah, no harm in that. One of the scariest jobs I had in implementing this was, we had a major highway that feeds our capital city just outside of our parliament, which, should we have ruined that, I wouldn't be here talking today. And we basically installed it over a conventional asphalt pavement. We did do a few repairs to make sure that the thing was fit for putting a good surfacing on. But yep, definitely can be done.
Just a sort of question aside from me, because Christchurch obviously suffers from earthquakes as well, is the material more resistant against lateral movement than traditional material?
No. Well, it probably is, but earthquakes are big things. The good thing is fault lines tend to go straight through roads. I mean, some of our fault lines have moved roads a couple of meters, so there's not much you can do about that. Things like lateral spreading around rivers, that will basically rip apart. Well, you don't need to worry about the surfacing, should we say. It's not the surfacing that's your problem.
Yeah, certainly I assume when you have large earthquakes or so, but I think I was more thinking of maybe sort of more minor things where you get more cracks in roads as opposed to lateral offsets.
Yeah, we haven't. Yeah, we didn't have too many sort of surfacing problems with conventional materials, and away from sort of places where we'd had liquefaction, so or fault movement. So yeah, it's conventional roads probably okay.
So questions are coming in thick and fast. So is it any more difficult to run the mixing epoxy spray bars in the field than with conventional spray bars? The question is particularly thinking about translating it to Ethiopia later.
Well, the little spray bar that we tested, that is actually just 2 paint pressure pots used to spray the components that they're just sitting in heated oil baths. So the answer is no. It's no harder to do. In fact, it is actually, if you can make a spray bar, you can certainly make one that will do this sort of work. It is about calibrating it and making sure you have calibrated it. But after that, it is just as hard as normal chip sealing, really. Not too hard.
Did it require quite a lot of operator training?
No, not really. So we were using our normal operators. So it is about having a system that will actually do what you want it to do. So yeah, the technology, it is effectively just making sure part A sprays out at the right rate and part B sprays out at the right rate, which is exactly what you're doing with the normal chip sealing operation. After that, no one actually knows that they're doing anything different. The chipping's the same, the rolling's the same, the traffic control is the same. It's pretty much the same.
Thank you very much. A few more questions. 25% epoxy means 25% of volume of bitumen?
It is 25% by mass of, and this is where it gets a little confusing in our naming convention. We're talking about 25% of the epoxy bitumens that you would buy for a bridge, blended in with 75% of your whatever you locally use for your bitumen. So in terms of the actual epoxy in there, that's actually, you write down at sort of the same sort of amounts of polymer that you're putting in, say, the SPSs. So there's very little actual epoxy in there that's doing the work. And that's an advantage, because if you use the bridge stuff and if you're a bit slow, you end up with big blocks of very solid stuff in the back of your truck, and everyone starts to get a bit upset. So the 25% stuff doesn't do that. You've got a number of hours to work with it, and it really doesn't set in a hurry. It just behaves very much like the conventional one, but when it gets cold, it's just annoying.
Good. Another question about the epoxy. Epoxy is a generic name. How do you specify the type of epoxy?
Yes, it's a very, very good question. We have specifically narrowed it down to a particular type of epoxies. So yeah, it's not every epoxy. You did right. It's a good question. If anyone wants a copy of our specification on what we have done, more than welcome to have that. The OECD's got some great stuff in their reports. That was fantastically done. They looked at a variety of different sort of epoxies, and yes, you can buy the wrong epoxy. Very definitely.
Can we use epoxy technology with continuously graded aggregate?
Yes. Yep. So that is very much what the bridge people do. Yep.
Another question about the behavior ultimately. Will the addition of epoxy not increase the stiffness of the asphalt mix, so making it prone to cracking?
Yeah, well, it increases the stiffness of the mix, but the fatigue performance of the epoxies is way outperforms your conventional mixes, way outperforms. So we've got papers that we've put to international journals showing our testing about 25%. The bridge stuff, the reason it is used is that it is highly fatigue resistant. That's its purpose on those orthotropic steel bridge decks.
As part of the work, have the New Zealand standards changed? Have you managed to get all this good results already in standard changes?
Well, we don't have a New Zealand standard for asphalt. We have a Waka Kotahi specification, and so yes, so that basically, yeah, we do our own specifications, so there isn't a New Zealand standard for this, or any asphalt for that matter. So
I think we've got one more question from Gemma. Gemma, do you want to ask it?
Hey, yeah, it won't let me type into the Q&A as a panelist. So, yeah, no, I just wanted to ask David. So, you know, we're looking at a 40-year surfacing life, which is unheard of, but obviously that's massive. So, I mean, obviously, the motorways in New Zealand, the ones where the OGPA has gone down in Auckland, have been very, very solidly built, but most of New Zealand is granular pavements. And I was just wondering sort of like what age pavements have you put the epoxy down onto? And are you kind of worried that your pavement might fail before the surface?
Yeah, it's a really good question. It's a really good question. Our average renewal rate in New Zealand is about 2%, you know, on a good year. So that
I was
suggests
going to say that's generous.
I know it's very generous at the moment, but historically it's been about 2%. So
yeah,
that would suggest that the average life of a pavement is around sort of 50 years. And so, yeah, we are right at the edge of it. The actual lab testing suggested that the epoxies could go on further, and we pretty much limited it to the minimum result that came out of the lab, because that sort of coincided with roughly what we thought we could get out of a pavement. So 40 years is what we sort of think a pavement can last. So yeah, there is a good question around, you know, is the pavement going to be good enough? But the thing is, we can actually build better pavements. You know, that is a matter of just deciding to do it.
I just wonder about putting it down on existing pavements that might not perhaps last that distance, or they might already be a bit old.
Yeah, so what we've been doing is pretty much putting it on our motorways. So it's, the porous asphalts are going down on our motorways. That's the idea with it. With the treatment using the epoxy chip seals, we're putting them on flushed sides, because the alternative on the flushed side is pretty much to the really badly flushed sites and the unstable chip seals. The alternative is to rip it all up. So at that point, it's actually a cheaper treatment than actually going and doing a full rehab. So it's a tricky one. And certainly when you're putting these surfacings on older pavements, you did right. That's that Wellington motorway example. We spent a lot of time looking at that and trying to work out how much life was left in that pavement before we actually got into it, because we were very nervous that we were about to spend good money on something that wasn't going to warrant it. So we actually did quite an extensive program of repairs prior to putting the epoxy down.
Thank you.
As time is coming quickly to an end, I'll try and get through the remaining questions. I think the answer to the sort of 25% epoxy blending, there's still a bit of uncertainty about what that meant. So there's another question whether you could repeat your answer or explain it, try and explain it again, please.
Right, okay. So right at the moment, out in the world, you can buy epoxy bitumen from suppliers like Kimco in the US. I believe there's, in Europe, you're getting it from whoever Shell's become. And there's a couple of other places that you can buy these materials from. And they're specifically for putting on orthotropic steel bridge decks. And there are standards around those epoxies around the world.
Yeah, I think it's the mixing ratio that is still uncertain.
Yeah, yep.
So what 25% means.
Yep. So the 25% means we use 25% by weight of those materials mixed with 75% of a local bitumen. So if I put 1 kilo of the epoxy bitumen from the bridge supplier into a pot, I then put three kilos of the conventional bitumen that I've got into a pot.
Thank you very much. As I said, last few questions, thinking of the time. If we apply epoxy modified asphalt with continuously graded aggregate, what about the advantage benefit as compared to porous asphalt?
What are the advantage benefit? I'd suggest you'll get a stiffer, stronger material out of it, without a doubt. So if you wanted to use this as some sort of structural layer, it would be a much stronger structural layer. We are only using it as a surfacing. We think that we haven't actually looked to see whether or not that would be a great idea. It could well be a genius idea for using that as a high fatigue layer. It's just time, money, and research effort. We've been concentrating on the thing that was causing us the biggest headache.
So there's a question on the sort of operation of the plant. So is it possible to get a document about the modification methods of the chip spreader, adding additional spray bars? Is there anything documented?
Yes, we've got some reports there. So yep, we can supply reports of what we've done. It's not particularly rocket science by any stretch of the imagination. So yep, we can provide that. The implementation for that full-scale one has been done on a full-scale computer-controlled sprayer, but yeah, the concept's not hard.
Okay, final question before I close. Could we provide timelines for the next steps for this program? So maybe that's over to you, Tunes.
Yep, thank you very much for that question. So yeah, we had a little bit of a shift to our original plan. We thought we're going to work first on the model development, but we felt it may be a better way to start calibrating the existing HDM models. We're progressing very well with that work. We're now in a stage of also looking at the adjustment for the Epoxy Modified technology for those models. So that will be ready for our HDM life cycle analysis early in the new year. And then at the same time, in parallel, we're also doing the development of alternative model forms. We are looking at perhaps incorporating some probabilistic model formats just to see what is going to be the most appropriate for this technology. So you may have noticed some of other panel members there is Associate Professor Joseph Costello, who's also involved with that study, and then our PhD student, Gemma Matheson. You've heard of her. Thank you.
Thank you very much. And I think this is an excellent timing. So it remains to me to say a big thank you to our panelists and also to our audience for their active participation. These were really excellent questions, and we had a fascinating discussion, and one I think that requires further development. I would also like to thank our funders, the FCDO and the HVT managers, IMC Worldwide, for providing support to the project that addresses climate change impact on transport systems, and the IRF for facilitating this webinar. We've obviously already discussed quite a lot today, and it's certainly fascinating from an academic viewpoint. But as you've seen, there's also real world impact, and that these materials are actually getting out and we're trialing them. So the CRISPS team will be organizing another webinar in early 2022, and we hope to see you all there in the new year. I guess it's now the right time to wish people a Merry Christmas as well, and also a Happy New Year. It's close enough now to be able to say that, I think. So thanks again to everybody for joining.